Okay, team, here we are. Back to some more lecture. We made it to isotopes the last time. And I just wanted to go over a few things with you over here on the Moodle front page. I have added a few things. There is now a link to online tutoring. That we do offer online tutoring. There is a tutoring schedule. And if you click on this Academic Learning Center, it says tutors are available. If you click that link, it takes you right into the Zoom meeting. Here are the hours, and you can see the different subjects. I would recommend contacting or checking the website here for details on who's tutoring when. Okay. Then we have a few other things. There is a Zoom link to my virtual office. My virtual office is open from 9 to 10 Monday and Wednesday. If you need to see me, if you have questions, you can just simply click on this link, and if it's between 9 and 10, there's a waiting room, and I'll let you in, and then we can have a little Zoom session, one-on-one, or there may be other people in the meeting. I don't really have any way of knowing who's going to be there, but I can certainly help you. Here is a link to your online textbook registration. So if you bought an ebook for your textbook, then simply click on this link. If you haven't already, you have 14 days to do it. And you don't have 14 days probably from the time you're watching this video. So be sure to register your textbook. And then here is a link to the AB Tech. This is my personal AB Tech Biology YouTube channel. And there's a botany playlist and there's a biology playlist. And of course, you're welcome to subscribe to the botany one as well. But your videos will be in the biology playlist. I'll try my best to have them organized. Typically, what I'll do is number them, and then also I will put test one info at the end of each video. If that's, I'll put whatever test it's pertinent to at the end of the video. So this is all important stuff for you to keep, to have access to. If you haven't already completed the syllabus verification, please do so. Okay. So we're going to pop back into this PowerPoint now. Let me scroll down. Oh, one other thing. All of these lecture tests are visible to you. You can see these on your Moodle. If I click on one, it gives you the dates when it opens. It says the quiz will not be available until Monday, September 14th. These are tentative dates. Please, if for some reason the test opens and we haven't finished the material, for example, please don't start taking the test. Let me give you the A-OK before you attempt a test, okay? Also remember, each week we have a lab. Here's lab one, the scientific method. Make sure that you turn one lab a week in, and it gives you the date that the lab is due. It's typically due, let's click on this one. It's typically due the Sunday, the night before, the Sunday of the week that, of that week. So Sunday at 11:55 p.m. Don't wait till the last minute, okay? Try and keep up with it. All right, so let's pop into the chemistry PowerPoint now. We were talking about isotopes before. And I want to say a little bit more about isotopes. Let's go back to the periodic table of elements for a second. Let's look at carbon. Carbon, remember, has an atomic number of 6 and an atomic mass of 12. Okay. So it is C612. And remember what these numbers indicate. The 6 indicates the atomic number, which is the number of protons. The 12 indicates the atomic mass, which is the protons plus the neutrons. What if I did this? C6H, I'm sorry, C or C14. What is this telling you? Well, it's telling you that there are extra neutrons in the nucleus of the atom, because now you do the math and you see, well, if this is the protons plus the neutrons and this is the protons, here we must have 8 neutrons instead of 6. Here we have 7, and then here is the stable form. So these are referred to as isotopes. Isotopes have extra neutrons in their nucleus, okay? So there's some interesting stuff about isotopes I want to share with you. They're unstable. That's one of the things to realize about isotopes. Okay. I'm a little sad because I recorded this entire video yesterday and I was sharing the wrong screen, and so it was just my pretty face the whole time. You couldn't see the screen, which was really annoying, but that's what happens sometimes. Okay, so isotopes. C14, C13, C12. The thing about isotopes is they're unstable and they give off neutrons. Right? So over time, this is time here, okay? And so over time, this C14 will get rid of a neutron, and then a little bit later, it'll get rid of another neutron, and it'll become C12. This is called the decay rate, okay? You may have heard of carbon-14 dating. It sounds like a dating site. It's not a dating site. It's a way to age something. Let's say that an archaeologist finds a bone in the ground and wants to know, you know, how old is this bone? How long has this bone been around? Well, what they do is that any bone, any living thing is basically a carbon-based thing, and a tiny percentage of the carbon is in the form of C14. If you know the decay rate over time and you find a bone, you can see how much C14 is left. And then you can do some mathematical equations and that tells you how old the bone is. Now, carbon-14 dating is good for things that are thousands of years old, up to maybe 40 or 50,000 years. But after that, there's no more C14 in the sample. And so then you wouldn't be able to know how old it was. They use other isotopes, radioactive isotopes, to determine the age of things that are older, like in the scale of millions of years. The other thing about isotopes, some of the larger ones are radioactive, right? And they can be dangerous. So if you think about plutonium, which is what we use, or uranium, plutonium is what we use to make nuclear bombs. Uranium we use in nuclear reactors, right? And so some of these isotopes have decay rates that are really long. We can talk about the half-life of an isotope. The half-life is, let's say you had a sample of uranium. Let's say you had 1 kilo of uranium. The half-life is how much time it takes to have a half kilo. And it turns out that for something like uranium, that's about 80,000 years. Okay, so what that means is if you have a kilo of uranium, 80,000 years later, you'll have half a kilo. So for this very long period of time, this stuff is dangerous, because what we know about radioactive isotopes is as they give off their neutrons, there's a lot of energy associated with it, and that energy can damage DNA. It's a mutagen. Okay, so you know, you look at nuclear power, for example, and you think, well, it has a very small carbon footprint compared to burning fossil fuels, which is a good thing. But what do we do with the nuclear waste? That's the question. And, you know, up to this point, we don't really have an answer. What we end up doing with it is storing it indefinitely. Usually we'll find some cave out in the in the desert and, or dig a hole in the desert and put it in there. So, this is an issue with radioactive isotopes like uranium that we use. We also use isotopes in medicine, for example, radiation therapy to treat cancer, or in imaging. And you might have had an upper or lower GI where they give you this big barium milkshake and they want you to drink it, and it's actually radioactive. They don't tell you that part. And as it gives off its neutrons, it allows you to visualize the gastrointestinal tract in that case. So isotopes can be used in medicine. They're certainly used to generate electricity or to generate power in nuclear power plants. And then we use them in archaeology or anthropology to date things and figure out how old they are. Okay. So if we go back to this periodic table, what we want to do now is we want to learn how to draw an atom. And that might seem weird. No one's ever even seen an atom, right? They're tiny, tiny things, but we want to know how to draw one. And the way that we're going to do that is using a system that it's like a shorthand for drawing an atom. And so let's look at a few of these different ones. Let's look at carbon and oxygen and sodium. Let's look at carbon and sodium for now. Okay. You'll notice hydrogen is 1 over here. It's the simplest element. Carbon is 6. Sodium is 11. Okay. Let me show you how we can do this in a drawing. So the way that we draw it, if we're going to do carbon, we know that the atom has a nucleus, and carbon, remember, is 6 and 12, so it has 6 protons and 6 neutrons in its nucleus. And then where are the electrons? Well, the electrons, the physicists tell us, are actually not in any one place. And what we do is we draw this little dotted line around the nucleus, and we call this an orbital. And an orbital is where the electrons may be at any given time. There's a rule about orbitals and electrons. The first orbital can only house 2 electrons, but the second, third, etc., can house up to 8 electrons. So the way we draw an atom, well, pretty straightforward. We know that if I'm not showing this as being charged, electrons are negative and protons are positive, so there must be 6 electrons if there's 6 protons in this case. And so we just draw them in, and we can fit 2. We usually draw them as little black dots like this. We can fit 2 in the first orbital. That's all it can hold. But we still have 4 left, and so we have to draw another orbital. And you just keep adding these orbitals until you've taking care of all your electrons. So now there's 2 and we have 4 more. 1, 2, 3, 4, and that accounts for the 6. 2, 4, 6. So that's a way that we could draw carbon. Okay. Makes sense? Let's draw another one. Let's draw sodium. Sodium is 11. Okay. So something like this. So here we draw the nucleus. And we have 11 protons and 11 neutrons, and now we have to put our electrons in the orbitals. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And now you'll notice there's 2, 4, 6, 8 in the second, and that's as many as will fit. What do we have left? Well, there's 11, so we have to draw a third orbital in here. Sometimes these orbitals are called shells, okay? and then we draw our last one. And so now let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so this is a shorthand for drawing an atom, and it's very useful. We'll see why in a second. Okay, so you could draw any of these. I mean, some of them are very large. Look, this one. Here's lead. It's 82. It has 82 electrons. You'd have to draw a whole bunch of shells in there, but you could do it, right? Okay. So now what we want to think about is, why do atoms react with one another to make what we call molecules, right? And what are some different kinds of chemical bonds that hold them together? And we actually have three basic types of chemical bonds. We have the covalent bond, where electrons are being shared, and we have the ionic bond, where electrons are being transferred. And then the third one is a hydrogen bond. It's kind of a different kind of bond, and we'll talk a little more about that in just a bit. Okay, so what is going on? There are some rules about why these molecules react with one another, or these atoms react with one another to form molecules. The rule is that atoms are not stable unless their outermost orbital is full of electrons. Think about what that's saying. Well, if it's only got one orbital, like say hydrogen, you know, it only has one electron, well, it needs a second one. If it has, if it's something like carbon, well, you know, it has to have 8 in its outermost orbital to be stable. This is why they react with other atoms to form molecules. So let's look at some examples of this. Okay, one example is called an ionic bond, and we can use this sodium that I've already drawn, and we can think about what we've learned. And what we've learned is that, you know, this outermost orbital, we call it the valence orbital, has to be full of electrons. Well, clearly here, we're not full. In fact, we only have one. We would need 7 more to be full, right? And so this one is, we have this 1 electron in the outer orbital. If you look at chlorine, it's 17 on the periodic table. So let's draw that right beside it. 17 protons, 17 neutrons. Now we have to put 17 electrons, 1, 2 in the first. 3, 4, 5, 6, 7, 8, 9, 10, and now we have 7 more. 1, 2, 3, 4, 5, 6, and 7. Okay, so now is chlorine stable? Well, almost. It has 7, it needs 8. And so what can happen is this one electron on the sodium can be transferred over here like this. Okay, and this is a transfer, and we call this an ionic bond. Okay, and so guess what? Now we have 8 for chlorine in its outer shell. What about this? Well, if we get rid of this 1 electron, remember that the orbital is just a hypothetical space. It's not really a structure. And so because of that, if we get rid of that 1 electron, then this orbital is now gone. Okay, and so now we count the electrons. I erased part of 1, and now we have 2, 4, 6, 8. Okay, so this is a really good example of an ionic bond. What have we made? NaCl, table salt, right? There you go, sodium chloride. Now, here's the thing. Does the electron just get transferred and then it's like ships in the night? You know, they go their separate ways? Not at all. It's a bond. There's an attraction now between these 2 atoms. And we want to just say a few words about what the attraction is. Well, here's the thing. It's all about the charge, right? We have 11 positive charges in the nucleus of sodium, but we got rid of a negative charge. See that? We only have 10 electrons. There's a net positive charge here because there's 11 protons but only 10 electrons, 11 positive charges, 10 negative charges. What that means is this molecule, this side of the sodium is positive. Okay, it has a positive charge. It's just the opposite over here. Here we gained a negative charge. We have 17 protons and 18 electrons. So this is negative. And what do you know about opposites? They attract, right? And so what holds sodium and chlorine together is this mutual attraction of the positive and the negative. And that's an ionic bond. It's a really good example of an ionic bond. It's a bond by the transfer of electrons from one atom to another. Okay? Let's think about a covalent bond. In a covalent bond, it's a different kind of bond. It's a bond by sharing electrons. Okay, so how does that work? Well, let's do oxygen. I'm going to draw oxygen now. And it is 8 and 16. Didn't really need to write the whole word out, I guess. Oh man, okay. Oh, 8, 16. Okay, so let's draw it. Let's see. We're going to say, here's the nucleus. We have 8 protons, 8 neutrons. There's 2 in the first shell. We have 8 altogether. So we need another orbital. 3, 4, 5. Is that right? 2, 4, 6, 8. Yeah, there's 8. Okay. So now you look at oxygen and you say, well, it's got 6 in its outer shell. It needs 2 more to be stable, right? Well, here's what can happen. Along comes a hydrogen. Hydrogen is 1. It only has 1 proton and 1 electron, like this. And then another hydrogen can come along. There's a hydrogen and oxygen. Another hydrogen can come along on the other side with its 1 electron. And what can happen is they can share electrons here. So this one gets shared and this one gets shared with the outermost shell of the oxygen. This is a hydrogen. And so what it would then look like is this. And now look, hydrogen with its 2, because it only has 1 shell, one orbital. There's 2 there. There's 2 there. And now let's count the oxygen's outer shell, 2, 4, 6, 8. So you see what they've done is they've just shared electrons here. Nothing's been transferred. They're literally sharing them to accomplish filling those outer orbitals. And what have we made? We've made H2O, right? And this is called a covalent bond. It's a bond by sharing electrons. Now, students inevitably ask me, how do I know if atoms are going to form an ionic bond or a covalent bond? And the truth is you may not know. But what I will tell you is they're going to do whatever's easiest. Whatever makes the most sense is probably how they're going to react. Now, covalent bonds are the kinds of bonds found in living things. Okay, so all of the chemical bonds that hold all of the molecules together in you are covalent bonds. One of the ways that we can draw a covalent bond is by a little dash like this. And you're going to see these little dashes over and over and over. Anytime you see one of these little straight lines, it indicates there's a pair of electrons being shared between adjacent atoms. Okay? So you're going to see this a lot when we start talking about organic compounds. There's going to be lots of these little lines. Always think of it as the sharing of electrons. We don't normally draw the little electrons over the line like that. I'm just showing you that. Okay. Now, quickly, before we move on into hydrogen bonds, molecules versus compounds. And what's the difference, right? Well, turns out that a molecule is simply two atoms stuck together. They can be the two atoms of the same element. For example, H2 or O2 are molecules, right? But are they compounds? They are not compounds. To be a compound, like water, you need at least two different elements. Okay, so here you have hydrogen and oxygen forming a molecule. All compounds are molecules, right? But all molecules are not compounds. Here you have two of the same elements stuck together like this, or like this. Okay, here you have hydrogen and oxygen, so water is in fact a compound. I point this out because we're about to talk about organic compounds in the next unit, and these are the building blocks of living things. Okay, so here's you may find this slide useful. It's just showing the ionic bond here. You had the transfer of this one. They're using X's and O's to represent the electrons of sodium and chlorine. And this is just basically what we looked like, what we just looked at. And here are some examples of covalent bonds. Here's carbon dioxide. You can see oxygen and two oxygens and a carbon come together. Huh. I don't know what that's about. No new notifications. Okay, well, how do I get rid of that? Oh, there it went. Okay. All right, so now we want to talk about water and some of the properties of water that make it very important. Here's the thing about water. Water, which we just saw, is formed by covalent bonds between oxygen and hydrogen. One of the most important things about water, one of its most important properties is that it has polarity. That's very important to understand. What does that mean? It has positive and negative sides, and the reason is because the electrons are skewed in this direction toward the oxygen. For whatever reason, the oxygen wants to possess those shared electrons a little more than the hydrogen. The result of that is that the oxygen part of water is slightly positively charged, and both of the hydrogens, are slightly negatively charged. Okay, and so what is the result of this is that water sticks to itself, and we call that cohesion. And so here's the thing about water, y'all. It forms what are called hydrogen bonds. Anywhere there's an oxygen on one water molecule, it's going to be attracted to the hydrogen on the other. And we usually do these little dotted lines to represent the hydrogen bonds. And you could go on and on and on and draw so many of these if you wanted. Okay. Ever wonder why rain falls as drops and not individual water molecules? Well, it's because of hydrogen bonding. Water sticks together. It sticks to itself. Cohesion means it sticks to itself. This is good because otherwise you'd be walking down the road. If water fell as individual water molecules, you'd be just walking down the road. You'd be like, oh, damn, it's raining. All of a sudden, you would just be wet. Okay. Instead, water falls as drops. This is why you can dive in a swimming pool, and the energy it takes to break the hydrogen bonds breaks your fall. You don't just crash to the bottom of the pool and crack your head open. This is why those water bugs can walk on the water. They're literally walking on the hydrogen bonds between water molecules. So water is very cool in that way. It also has adhesive properties. And by adhesion means it sticks to charged things like glass. Okay, so adhesive properties means that if something is charged, it will stick to it. If you take two pieces of glass and you put some water between them and try and pull them apart, you find this out very quickly, right? Water sticks, makes it hard to pull the glass apart. There's an old bar trick where you take a shot glass, you fill it up with water to the very top, right? And then you bet somebody that you can drop 2 quarters in it without any of the water spilling. And they're like, no way, the water's going to spill. And so what happens then is you drop the quarters in and you get this kind of thing going here. The water's sticking to itself, and it's also sticking to the edges of the charged glass. You got to make sure the shot glass is glass, not water. And so then you can, you make your $50 there. Okay. So these are all properties of water. The other property of water is called specific heat. And specific heat ends up being very important to living things because remember homeostasis, because of the hydrogen bonding, water has a very high specific heat, meaning it resists changes in temperature, right? Water heats up and slows down much more slowly than something like metal. And that means it has a very high specific heat. This allows us to maintain homeostasis. We don't heat up or cool down too fast because we're mostly made of water. If we were made of metal, we wouldn't have a way of really regulating our temperature as well. Okay, so these are all important things about water. Okay. And you can see in this image, there's there's these dotted lines showing the slightly negative and slightly positive sides of the water molecule wanting to stick together. Okay. Now we get to the pH scale. And we'll talk about the basic scale first, and then we will talk about what pH really is mathematically a measure of, because it is a mathematical measurement. You'll notice it says that freshly distilled water has a pH of 7. 7 is neutral on the pH scale. And this actually goes from 0 to 14. So there's a couple of numbers missing, but it does say that here. Okay. So pure water is neutral. As we get lower, it becomes more acidic. And as we get higher, the numbers become more basic. Okay, so for some reason, students switch these around a lot. So remember, lower numbers are acidic, higher numbers are basic. And you can see some pHs of random things. You'll notice carbonated beverages are very acidic. They're only slightly less acidic than lemon juice. And carbonated beverage is even more acidic than vinegar. And this is why if you drink a lot of carbonated beverages, they can damage your teeth. You can see vinegar, orange juice, beer, coffee. You'll notice that blood and milk are almost neutral. Remember, we said that pH is a homeostatic mechanism that's controlled in living things. So it would make sense that your blood would be close to being neutral because life exists in a relatively neutral pH. The reality is if your blood gets acidic, it kills you. You can't live very long. I'd like to point out that the most acidic rainfall ever recorded was recorded on Mount Mitchell which is not far from here. If you go on the Parkway north, you get to Mount Mitchell. It was about a 2.5, which is almost the acidity of lemon juice. Okay, very, very acidic acid rain, most acidic rainfall ever recorded. And this is due to particulate matter in the air, usually from burning fossil fuels like coal. Nitrates particularly cause the rain to become very acidic, and it has a detrimental effect on wildlife and plants especially. Okay, so you know that things that are really acidic can burn you, like gastric juice. If you've ever thrown up, which you all have, you know it burns your throat. Very acidic things can certainly burn you. What about very basic things? Can you be burned by something basic? Absolutely. We refer to them as being caustic. For example, lye, which is the active ingredient in Drano. It tells you right on the Drano, you know, don't get this stuff on your skin and then get it wet, because that activates it and it'll burn a hole in you. So what is it really a measure of? What is pH? Let's talk about it. Here's the thing about water, y'all. Water, it seems appropriate I'm using this color, I guess. I don't know. Water is constantly doing this. And this is referred to as dissociation. And what we mean by that is, if you look at a sample of water, there's a small portion of the water that disassociates. These positively and negatively charged things are called ions. And so we need to know this word ion is a charged particle. And now, given what you know about atoms, you know if it's positively charged, it must have an extra proton. And if it's negatively charged, it must have an extra electron, right? And so water is kind of a shapeshifter. It's constantly shifting back and forth between its normal form and these ions. And you can see if you add these together, it makes water, right? HOH. So here's the thing. If we measure the concentration of hydrogen ions in pure water, the number that we get is 1 times 10 to the negative 7. That's a very small number, right? So what is pH a measure of? pH mathematically is the negative log of the concentration of hydrogen ions in solution. Okay, well, for pure water, where do we get the 7 as the pH of pure water? Well, it's right here, isn't it? It's the negative log of the concentration of hydrogen ions in solution. For pure water, what's the log? The log is the exponent. So negative 7 is the log. If we take the negative of that, it becomes 7. Okay. That's how you determine, that's where the 7 came from. The 7 isn't arbitrary. It's an actual mathematical number. It's the negative log of hydrogen ions. Now, it should make sense to you that if in pure water, the concentration of hydrogen ions is 1 times 10 to the negative 7, then these are called hydrogen ions, and these are called hydroxyl ions. I should have told you that before. This is a hydroxyl, and this is a hydrogen. Okay. It should make sense that this is the same number, right? This is also 1 times 10 to the negative 7, because there's 1-to-1 relationship. For every one of these, you're going to get one of these if you're talking about water. Okay, so these are equal in pure water, and the concentration is 1 times 10 to the negative 7% of of the sample of water. Okay, so then what in the world, how do we know if something is an acid or a base? Well, pretty simple. If you take something and you put it in pure water, and you get an excess of hydrogen ions, it's an acid. And if you get an excess of hydroxyl ions, it's a base. It's really that simple. So let's take some hydrochloric acid, HCl. And you know it's an acid, it's called hydrochloric acid, right? But if you dump that in water, it dissociates and you get this. So is hydrochloric acid an acid or a base? Well, you're getting an excess of hydrogen ions, that makes it an acid. Okay, what if you dump some sodium hydroxide in some water? What happens? Well, it dissociates and you get Na plus OH minus. Now you're getting an excess of hydroxyl ions, and so that makes sodium hydroxide a base. It's pretty simple. Take your sample, dump it in water. If you get hydrogen ions in excess, it's an acid. If you get hydroxyl ions in excess, it's a base. Okay. Now, one last thing to mention about the pH scale, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14. This is an exponential scale, not a linear scale. Now, what does that mean? 7 is neutral. And so rather than 5 being 2 times more acidic than 7, it's actually exponential. So this is 10, 100, 1,000, right? So a pH of 4 is 1,000 times more acidic than 7, not 3 times more acidic. What about a pH of 7 to 10? Well, 10 is how many times more basic? 10, 100, 1,000 times more basic, right? So it's important to realize that the pH scale is not a linear scale, it's an exponential scale. You're going to do a lab that's going to help, I think, at understanding this stuff. That is actually the end of the lesson, I believe. And we will pick up where we left off. What we have left to do now is to talk about organic compounds. Organic compounds are the building blocks of living things. And once we know what living things are made out of, we can rationally discuss living things. And that means we can talk about cells, because the cell is the smallest unit of life. Okay. Hope you have a great day. I've enjoyed lecturing to you today, even though I had to do it twice because of my forgetting to record the last time. But hopefully this one works out. And I will see you all soon, I hope. Take care.